We already covered the theory of the 6 cases. Now we apply it. 30 factoring problems, from easy to hard, solved step by step. Grab a pencil and paper, we learn by doing. Let's begin. Let's start with a warm-up. Let's factor 4x² minus 8x. 2 terms, and both share something. A 4 fits into 8, and x is in both. The greatest common factor is 4x. We pull it out. Now we divide. 4x² over 4x is x, and 8x over 4x is 2. So we get 4x times x minus 2. Quick check. Multiplying back. 4x times x is 4x², and 4x times 2 is 8x. The original came back. This one is elegant. Let's factor x² minus 49. 2 terms and a subtraction. The key clue, both are perfect squares. x² and 49, which is 7 squared. We take the root of each. Root of x² is x, and root of 49 is 7. And a difference of squares always opens into a sum times a difference. X plus 7 times x minus 7. Check. X plus 7 times x minus 7. The middle terms, plus 7x and minus 7x, cancel, leaving x² minus 49. Now a trinomial. Let's factor x² plus 8x plus 15. 3 terms and x² goes alone, with no number in front. That's the friendliest case. We look for 2 numbers that add up to 8 and multiply to 15. Think 3 and 5. 3 plus 5, 8. 3 times 5, 15. O's 2. So each number goes with x. X plus 3 times x plus 5. Check. X times x. x². The middle term 5x plus 3x. 8x. And 3 times 5, 15. This one looks uglier, but watch how nicely it works. Let's factor 2x² plus 7x plus 3. 3 terms, but careful. Now x² does have a number in front, a 2. There we use the a times c method. We multiply the ends. A times c, 2 times 3, 6. And we look for 2 numbers that add to 7 and multiply to 6. There's 6 and 1. With them we split the middle term. 7x becomes 6x plus x. Now we group in pairs and pull the common factor from the first, 2x times x plus 3, from the others, 1 times x plus 3. X plus 3 repeats, so we get 2x plus 1 times x plus 3. Check. 2x times x, 2x², the middle, 6x plus x, 7x, and 1 times 3, 3. Perfect. We close the batch with a perfect square in disguise. Let's factor 9x² minus 12x plus 4. 3 terms, and the 2 ends are perfect squares, 9x² and 4. That smells like a binomial squared. We take the root of the ends. Root of 9x² is 3x, and root of 4 is 2. But before trusting it, the golden test, 2 times 3x times 2 must give the middle term. And it gives 12x. It matches. Since the middle term is negative, inside goes a minus. So it's 3x minus 2, all squared. Check. 3x minus 2, squared. The first squared, 9x², the double product, minus 12x, and the second squared, 4. Now we start combining techniques. Let's factor x³ minus 4x. 2 terms, but first of all, the golden rule. Always check for a common factor and take it out first. Here x is in both terms, so we pull out x, and inside we're left with x² minus 4. And look what's inside. x² minus 4 is a difference of squares, which opens into x plus 2 times x minus 2. So the full result is x times x plus 2 times x minus 2. Check. X plus 2 times x minus 2 gives x² minus 4, and that times the x outside gives x³ minus 4x. Let's keep going with another combined one. Let's factor 3x² minus 27. At first glance, it doesn't look like a difference of squares, because 3 isn't a perfect square. But the rule is the same. Check first for a common factor. 3 fits into both. 3 times 9 is 27. We pull out the 3, and inside we get x² minus 9. And what's left inside is a difference of squares, x plus 3 times x minus 3. So we get 3 times x plus 3 times x minus 3. Check. X plus 3 times x minus 3 gives x squared minus 9, and that times 3 gives 3x squared minus 27. This one is beautiful. It's a difference of squares that factors twice. Let's factor x to the fourth minus 81. Both are perfect squares, x to the fourth and 81, which is 9 squared. We take roots. Root of x to the fourth is x squared, and root of 81 is 9. We get x squared plus 9 times x squared minus 9. But watch the second parenthesis. X squared minus 9 is again a difference of squares, so we open it. X plus 3 times x minus 3. The first parenthesis, x squared plus 9, is a sum, and a sum of squares can't be factored over the reals. It stays put. The final answer has 3 factors. Let's check in parts. X squared plus 9 times x squared minus 9 already gives x to the fourth minus 81. The original came back. Now we mix common factor with a trinomial. Let's factor 2x cubed plus 10x squared plus 12x. 3 terms, and all 3 share something. A 2 fits in all, and x is in all too. The common factor is 2x. We pull it out, and inside we get a friendly trinomial. X squared plus 5x plus 6. There we look for 2 numbers that add to 5 and multiply to 6. They're 2 and 3, 2 plus 3, 5, 2 times 3, 6. Each number goes with x, and we don't forget the 2x outside. We get 2x times x plus 2 times x plus 3. Check. X plus 2 times x plus 3 gives x squared plus 5x plus 6, and that times 2x brings back the original. We close the batch with 1 with negatives, which looks scary but comes out clean. Let's factor 6x squared minus x minus 15. 3 terms, and x squared has a number in front, a 6. There we use the a times c method. We multiply the ends. A times c, 6 times minus 15 is minus 90, and we look for 2 numbers that multiply to minus 90 and add to minus 1. They're minus 10 and 9. With them we split the middle term. Minus x becomes minus 10x plus 9x. We group in pairs and pull the common factor. From the first, 2x times 3x minus 5. From the others, 3 times 3x minus 5. 3x minus 5 repeats, so we get 3x minus 5 times 2x plus 3. Check. 3x times 2x, 6x squared. The middle, 9x minus 10x minus x, and minus 5 times 3 minus 15. We start the hardest batch with a quick one that has a trick. Let's factor x squared y minus xy squared. 2 terms, and notice that now 2 letters repeat. X is in both, and y is in both too. From each letter we take the lowest power, 1x and 1y. The common factor is xy. Now we divide. X squared y over xy is x, and xy squared over xy is y. So we get xy times x minus y. Check. Xy times x squared y, and xy times minus y minus xy squared. The original came back. This one combines 2 cases, and it all happens with letters. Let's factor eta cubed minus 2ab squared. 2 terms, and again the golden rule. First of all, pull the common factor. Both have a 2, and both have an a. The common factor is 2a. We pull it out, and inside we get 4a squared minus b squared. And look inside. Even though it's all letters, it's a difference of squares. The root of 4 squared is 2a, and the root of b squared is b. It opens into 2a plus b times 2a minus b. The full result is 2a times 2a plus b times 2a minus b. Check. 2a plus b times 2a minus b gives 4a squared minus b squared, and that times 2a brings back a cubed minus 2ab squared. This is one of my favorites because it looks like university level and comes out with a lovely trick. Let's factor x to the fourth minus 5x squared plus 4. The trick is to look at x squared as if it were a single thing. We give it a name, u. Then x to the fourth is u squared, and we get u squared minus 5u plus 4. And that's a friendly trinomial, 2 numbers that add to minus 5 and multiply to 4. They're minus 1 and minus 4. We get u minus 1 times u minus 4. Now we put x squared back in place of u. We get x squared minus 1 times x squared minus 4. But we're not done. Each parenthesis is a difference of squares. X squared minus 1 opens into x plus 1 times x minus 1, and x squared minus 4 into x plus 2 times x minus 2. The final answer has 4 factors. Let's check in parts. X squared minus 1 times x squared minus 4 already gives x to the 4th minus 5x squared plus 4. This one has 4 terms and a hidden treasure. Let's factor x squared plus 2x plus 1 minus y squared. With 4 terms we think about grouping, but not just any way. Look at the first 3. We split them off. X squared plus 2x plus 1 and separately minus y squared. And here's the treasure. The first 3 are a perfect square trinomial. The roots of the ends are x and 1, and the double product gives 2x. So x squared plus 2x plus 1 is x plus 1 squared. Now everything became x plus 1 squared minus y squared. And that's a difference of squares. It opens into x plus 1 plus y times x plus 1 minus y. That's the result. Check. X plus 1 squared is x squared plus 2x plus 1, and we subtract y squared. The original came back. We close the batch with one where you must be very careful with signs. Let's factor 4x squared minus the whole binomial x minus 3 squared. It looks odd, but it's a subtraction of 2 squares. 4x squared is 2x squared, and the other one already comes squared. We apply the formula with roots 2x and the binomial x minus 3. We get 2x plus the binomial times 2x minus the binomial. And here's the care. When we subtract the binomial, the minus goes into both. 2x minus x minus 3 is 2x minus x plus 3, that is x plus 3. And on the other side, 2x plus x minus 3 is 3x minus 3. We get 3x minus 3 times x plus 3. We can still go further. In 3x minus 3 there's a common factor 3, which comes out and leaves x minus 1. The clean result is 3 times x minus 1 times x plus 3. Check. X minus 1 times x plus 3 gives x squared plus 2x minus 3, and that times 3 gives 3x squared plus 6x minus 9, which is exactly 4x squared minus the binomial squared. We enter the home stretch, and this one combines 2 cases. Let's factor x cubed plus 3x squared minus 4x minus 12. 4 terms, so we think about grouping in pairs. We split them, the first 2 on one side, and the last 2 on the other. From the first, we pull x squared, leaving x plus 3. From the last, we pull minus 4, leaving x plus 3 again. Since the same binomial, x plus 3, repeats, we pull it out as a common factor, and inside we get x squared minus 4. But we're not done. X squared minus 4 is a difference of squares, which opens into x plus 2 times x minus 2. The final answer has 3 factors, x plus 3 times x plus 2 times x minus 2. Let's check in parts. X plus 3 times x squared minus 4 already brings back x cubed plus 3x squared minus 4x minus 12. We continue with a difference of squares that factors twice with a hidden common factor. Let's factor 2x to the 4th minus 32. First of all, the golden rule. Check for a common factor. Both terms have a 2. 2 times 16 is 32. We pull out the 2, and inside we get x to the 4th minus 16. And that's a difference of squares. The root of x to the 4th is x squared, and the root of 16 is 4. We get x squared plus 4 times x squared minus 4. But watch the second parenthesis. X squared minus 4 is again a difference, opening into x plus 2 times x minus 2. The first parenthesis, x squared plus 4, is a sum of squares, and that can't be factored over the reals. It stays put. The final answer carries the 2, the sum that won't open, and the 2 binomials. Let's check in parts. X squared plus 4 times x squared minus 4 gives x to the 4th minus 16, and that times 2 brings back 2x to the 4th minus 32. Now a couple of fractions, which look terrifying but melt away once you factor. Let's simplify. X squared minus 9 over x squared minus 6x plus 9. The trick is always the same, factor top and bottom, and cancel whatever repeats. On top, x squared minus 9 is a difference of squares, x plus 3 times x minus 3. And on the bottom, that trinomial is a perfect square, x minus 3 times x minus 3. We rewrite the fraction already factored. And here's the nice part, the factor x minus 3 is on top and bottom, so it cancels. We're left with x plus 3 over x minus 3. Let's do another fraction, very similar, to nail the method down. Let's simplify x squared minus 1 over x squared plus 2x plus 1. Same move again, factor top and bottom, and cancel. On top, x squared minus 1 is a difference of squares, x plus 1 times x minus 1. And on the bottom, it's a perfect square, x plus 1 times x plus 1. We rewrite it already factored. The factor x plus 1 repeats top and bottom, so it cancels. We are left with x minus 1 over x plus 1. And we reach the final boss. Let's simplify this whole expression. 2x squared plus 7x plus 3 over x squared plus 6x plus 9 times x plus 3 over 2x plus 1. Let's breathe. The strategy is to factor absolutely everything and then cancel. The numerator of the first 2x squared plus 7x plus 3 factors as 2x plus 1 times x plus 3. And the denominator, x squared plus 6x plus 9, is a perfect square, x plus 3 times x plus 3. Now we multiply the two fractions into a single one. On top we get 3 factors, and on the bottom another 3. And watch the magic. The factor 2x plus 1 on top cancels with the 1 below, and x plus 3 on top cancels with 1 below, and the last x plus 3, 2. Absolutely everything cancels. And when everything cancels, 1 is left on top and 1 on the bottom. The answer is simply 1. We open a new and very elegant type, completing the square, to reach a difference. Let's factor x to the 4th plus x squared plus 1. Look closely, the first and last terms are perfect squares. The root of x to the 4th is x squared, and the root of 1 is 1. But there's a detail. If this were a perfect square, the middle term would have to be 2x squared, and we only have 1. That's the trick. We complete the square by adding and subtracting what's missing. The square we want is x squared plus 1 squared, which gives x to the 4th plus 2x squared plus 1. Since we have 1x squared and need 2, we add an x squared, and to change nothing, we also subtract it. The first 3 now form the square, x squared plus 1 squared, and what we subtracted, x squared, is another square. That's a difference of squares which opens into 2 parentheses. Reordering, we get x squared plus x plus 1 times x squared minus x plus 1. Check. Multiplying the 2 parentheses, the terms with x cubed and with x cancel, leaving x to the 4th plus x squared plus 1. We keep the same trick in a famous case. Let's factor x to the 4th plus 4. Notice there are only 2 terms, and there isn't even a middle term. But both are squares, x to the 4th and 4, which is 2 squared. The square we want is x squared plus 2 squared, which gives x to the 4th plus 4x squared plus 4. We're missing the 4x squared in the middle, so we add it, and to change nothing, we also subtract it. The first 3 build the square, x squared plus 2 squared, and what we subtracted, 4x squared, is 2x squared. That's a difference of squares. Reordering, we get x squared plus 2x plus 2 times x squared minus 2x plus 2. Check. The 2 parentheses are equal except for the sign of 2x, so when we multiply, everything in the middle cancels, leaving x to the 4th plus 4. Let's do a similar one to nail the method down. Let's factor 4x to the 4th plus 1. Again 2 terms, and again both are squares. The root of 4x to the 4th is 2x squared, and the root of 1 is 1. The square we want is 2x squared plus 1 squared, which gives 4x to the 4th plus 4x squared plus 1. We are missing the 4x squared in the middle. We add it, and to compensate, we also subtract it. The first 3 form the square, 2x squared plus 1 squared, and what we subtracted, 4x squared, is 2x squared. Difference of squares. Reordering, we get 2x squared plus 2x plus 1 times 2x squared minus 2x plus 1. Check. Since the parentheses only change the sign of 2x, everything in the middle cancels when multiplying, leaving 4x to the 4th plus 1. We closed this type with a two-letter one, beautiful and very symmetric. Let's factor a to the fourth plus a squared b squared plus b to the fourth. The first and last are perfect squares, a squared and b squared raised. The square we want is a squared plus b squared squared, which gives a to the fourth plus 2a squared b squared plus b to the fourth. The middle would have to be 2a squared b squared, and we only have 1. So we add 1a squared b squared, and to change nothing, we also subtract it. The first three form the square, a squared plus b squared squared, and what we subtracted, a squared b squared, is a b squared. Difference of squares. Reordering, we get a squared plus a b squared times a squared minus a b plus b squared. Check. When multiplying, the terms with a cubed b and with a b cubed cancel, leaving a to the fourth plus a squared b squared plus b to the fourth. We return to fractions, which we already know how to melt by factoring. Let's simplify. X squared plus 5x plus 6 over x squared minus 4. The trick is always the same, factor top and bottom, and cancel whatever repeats. On top, that trinomial factors by finding two numbers that add to 5 and multiply to 6, they're 2 and 3, so we get x plus 2 times x plus 3. And on the bottom, x squared minus 4 is a difference of squares, x plus 2 times x minus 2. We rewrite the fraction already factored. And here's the nice part, the factor x plus 2 is on top and bottom, so it cancels. We're left with x plus 3 over x minus 2. We close the batch with a fraction that hides several cases at once. Let's simplify. X cubed minus x over x squared minus 2x plus 1. Same move again, factor top and bottom, and cancel. On top, first we pull the common factor x, leaving x times x squared minus 1, and that parenthesis is a difference of squares, x plus 1 times x minus 1. So on top we get x times x plus 1 times x minus 1, and on the bottom, that trinomial is a perfect square, x minus 1 times x minus 1. We rewrite it already factored. The factor x minus 1 repeats top and bottom, so 1 cancels with 1. We are left with x times x plus 1 over x minus 1. New error. Here come the word problems where factoring is actually useful. Let's start with geometry. A rectangle's area is x squared plus 7x plus 12. And the question is, how long are its sides? The key is to remember that a rectangle's area is length times width. That is, a product. So if we factor the area, we get the two sides directly. It's a simple trinomial. We look for two numbers that add to 7 and multiply to 12. They're 3 and 4. So the area factors as x plus 3 times x plus 4. And there's the answer, but in context, the rectangle's sides measure x plus 3 and x plus 4. Second problem, solving an equation for which values of x is x squared minus 5x plus 6 equal to 0. The trick is to factor the left side and then use a very powerful property. The trinomial factors by finding two numbers that add to minus 5 and multiply to 6, they're minus 2 and minus 3. We get x minus 2 times x minus 3 equals 0. And here's the jewel. If a product of two things is 0, then one of them must be 0. There's no other way to get 0. So either x minus 2 is 0, giving x equals 2, or x minus 3 is 0, giving x equals 3. The answer, x equals 2 or x equals 3. Those are the two values that make the equation true. We step up, same idea, but now with a number in front of x squared. Let's solve 2x squared plus 5x minus 3 equal to 0. Again, the plan is to factor and use the zero product. But since there's a 2 in front, we factor with the a times c method. We multiply a times c, 2 times minus 3 minus 6. We look for two numbers that add to 5 and multiply to minus 6, they're 6 and minus 1. Splitting the middle term and grouping the trinomial factors, we get x plus 3 times 2x minus 1 equals 0. So either x plus 3 is 0, giving x equals minus 3, or 2x minus 1 is 0, giving x equals 1/2. The answer, x equals minus 3, or x equals 1/2. And we close the 30 with a beautiful problem. From a large square of side x, we cut a tiny square of side 4 out of one corner. The remaining area is x² minus 16. The task: write the area as a product. Notice two terms as subtraction, and both are perfect squares. x² and 16, which is 4 squared. It's a difference of squares. We take the root of each. Root of x² is x, and root of 16 is 4. And a difference of squares always opens into a sometimes a difference, x plus 4 times x minus 4. In context, the remaining area is x plus 4 times x minus 4. And with this lovely problem, we close all 30 exercises. And with that, we close all 30 problems from the simplest common factor all the way to the word problems where factoring solves something real. If you made it this far, your eye is now trained to recognize and factor almost anything. If these problems helped you, subscribe and ring the bell so you don't miss the next challenges. Practice a lot, because factoring is learned by factoring, and see you in the next video.